Did you give me the product I requested?
Yeah, man, I got that Mary Sharp's hot sauce right here for you, man. It'll just be $1.
Alright, man, there you go.
Thanks. Where's the tax?
What do you mean?
There's sales tax, 11-cent sales tax.
Dude.
Please.
Here is 6 pennies and a nickel.
Okay. Did you not have like a dime and a penny you could give me? Like, this is a lot of change.
Okay, so I didn't give my friend the amount of change that he wanted in the correct values. He wanted a dime and a penny, which would be the largest amount that I could give him, or the least amount of change that I could give him, and I gave him a nickel and 6 pennies, which was incorrect for him. So thankfully, the change-making algorithm is an algorithm that we can use that will show us the amount that we will need to use the least amount of coins possible. So, given an amount, and we'll just call this amount N, which in our case was the 11 cents needed. We'll find the least amount given the coin denominations that are D1, which is less than D2, which is less than, and this can go on and on for the amount of coin denominations all the way to D sub M. And M stands for the coin amount, or the number of coin denominations. So the change-making algorithm takes our given amount N, which is 11 cents, and then uses the coin denominations D1 through Dn, which is our number of coin denominations, and it comes out with the result. So our coin denominations in this case would be a penny, a nickel, and he wanted a dime, so we'll also include a dime, which would be 1, 5, and 10. So we have 1, 5, and 10, and these are our coin denomination amounts, and we need 11 cents. So given these amounts, what would we use to make 11 cents with the least amount possible? Well, you could say we would just use a dime and a penny, which would be correct. But how do we go about doing that within this algorithm? So I'll go ahead and show you. So since this algorithm is using dynamic programming, it's going to take up a little bit more space. And we're going to make an array that will take up the space, but it will be shorter time-wise, so have a better time efficiency. So the first thing we're going to say is, what is our input? Our input is going to be equal to 11 for the cents, so 11 cents. And then our coin denominations, as I said earlier, are going to be 1, 5, and 10. So given our input and our coin denominations, we can use this algorithm to figure out how many we would need. So given these, what is our first step? So step 1, we're going to create an array. Of size. And this input is all, we're going to use the value in to represent. So our input is in. So we want to create an array of size n plus 1. So let's go ahead and make our array. Alright, so now that we have our array, let's go ahead and label our index values. And what these index values actually represent is the number of coins. So say we need 11 cents, and this is 11 cents, and what will go in here is how much, or how many coin denominations we will need to make 11 cents. So as we said earlier, 1 and 10 would make 11. So what would go in here would be 2. But I'll show you how we find that value using the algorithm. But just realize that, you know, if we're making 0, we're going to go ahead and call this array f. And if we're making 0, then we don't have any coin denominations that we need, so this will automatically be 0 for our first initial value. And let's go ahead and have this keep track of our index values. We're going to start that at 0. So when f sub I is equal to, when f sub I is equal to 0, it's going to be equal to 0. So we'll go ahead and erase this. So when f of 0 will be equal to 0. So you're probably asking, what is our formula that we will need for a change-making algorithm to make it work? All right, so now that we have our input and our coin denominations and our array made, let me explain what's going on here a little bit. So this is going to keep track of our index with I, and f of 0 is going to be equal to 0. So I went ahead and put that into the value there. So f sub I is going to be equal to the minimum of f I minus our first coin denomination, which is 1, or f I minus our second coin denomination, which is 5, or f I minus our third coin denomination, 10. Close this off, and then we want to add 1. So this is our formula that we'll use for the algorithm to calculate each of these values. And you're thinking, well, I could just do this, you know, in my head for how much change I would need for 11 cents, but when you get to larger numbers, you can see the usefulness of this. So we'll go ahead and get started. So for our first value, f of 1, we'll go ahead and change our I from 0 to 1, increment it. So we'll also change it here. So at f of 1, the minimum of 1 minus 1 is going to be 0. And then for any value where it's going to be negative, we just don't include it. So 1 minus 5 is negative 4, and 1 minus 10 is negative 9. So we're not going to include these. So it's just going to be 0. And then plus 1. So that's going to be equal to 1. So the value that goes here is 1. And we can see that if we have 1 cent and we're using these coin denominations, the amount of change that we would use would be 1. Hence why it goes there. So if we go ahead and increment that again, put I of 2, f of 2, and this is going to be 2 minus 1, which is going to be equal to 1. 2 minus 5 is going to be equal to negative 3, so we won't use that. And 2 minus 10 is going to be equal to negative 8, so we're not going to use that. So we have 1 plus 1, which is going to be equal to 2. So 2 is going to go into our value here. We'll take coin denominations, 2 ones to make a 2. And then we'll go ahead and increment I again. So I is going to be equal to 3. So f of 3 will be 3 minus 1, which is going to be 2. 3 minus 5 is negative 2, so we won't use that. 3 minus 10 is negative 7, so we won't use that. And then we'll add 1. So 2 plus 1 is going to be equal to 3. And we'll go ahead and put that into the value here. Then we'll increment I again. So at f of 4, we'll do 4 minus 1, which is 3. 4 minus 5 is negative 1, so we won't use that. 4 minus 10 is negative 6, so we won't use that. So it's going to be 3 plus 1, it's going to be 4. It's going to take out of the coin denominations 4 ones to make the 4, so 4 goes there. Then we'll go ahead and increment I again. So f of 5, the minimum would be 5 minus 1, which is 4. And then we can actually use this one now because 5 minus 5 is 0. So it's going to be 0. And then 5 minus 10 is negative 5, so we're still not going to use this one. But we have these two options. So what is the minimum value? 4 is 0, so it's going to be 0, right? So we'll choose 0, and then we'll do 0 plus 1 is equal to 1. So 5 is going to be equal to 1. Like I said, instead of using all these 1s from the coin denomination, we'll use the 5. So you just need 1 5 to make a 5, so hence why that's 1. And then we'll go ahead and increment again. I is equal to 6. F of 6 is the minimum. 6 minus 1 is 5. 6 minus 5 is 1. 6 minus 10 is negative 4, so we won't use that. The minimum value out of these two is going to be 1. So we'll choose 1. And then 1 plus 1 is going to be equal to 2. So we'll put 2 here. 5 plus 1 is 6. So 5 and 1 are the coin denominations. We'll go ahead and increment I again to 7. So f of 7 is going to be 7 minus 1, which is 6. And then 7 minus 5 is 2. And then 7 minus 10 is negative 3, so we won't use it yet again. Smallest value here is going to be the 2. So we'll do 2 plus 1, which is 3. And we'll need 5 and 2 ones, hence 3. And then we'll go ahead and increment I again to 8. F of 8, the minimum of f is going to be 8 minus 1, which is 7. Or 8 minus 5, which is 3. And then 8 minus 10 is negative 2, so we won't use it. So the smallest value here is going to be 3. And then we're going to do 3 plus 1, which is equal to 4. We'll put 4 in this box here. And then 5 and 3 ones, which is 4 coins from the denomination. And we'll go ahead and increment I. F of 9 is going to be 9 minus 1, which is going to be 8. And then 9 minus 5, which is going to be 4. 9 minus 10 is negative 1, so we still won't use that. Our smallest value is 4. So we'll do 4 plus 1, which is equal to 5. And we'll put 5 in the value here. 5 and 4 ones, so 5 coins. And we'll go ahead and increment I to 10. f of 10. It's going to be f of 10 minus 1, which is 9. And then 10 minus 5, which is 5. And then we can actually finally use the minus 10 here. So 10 minus 10 is 0. So we're using all of these values. And we can see that 0 is the smallest, so we'll use 0. Then we'll do 0 plus 1, which is equal to 1. And this is going to be 1. And that's because our coin denomination, we finally got to this 10, this dime here. And to make 10 cents, we only need one coin, which is the dime. And we'll increment I to 11. All right, so I is 11. We'll change it to f of 11. So at 11, we have f of 11 minus 1, which is 10. F of 11 minus 5, which is 6. And then f of 11 minus 10, which is 1. And then we can see that 1 is the smallest here, so we're using the minimum. And then 1 plus 1 is equal to 2. And that is a dime and a penny to equal 11 cents. And in this array, we can find the number of coins needed, or the answer will be the value that is held in the last value of the array. So we see 2 is going to be the number of coins we need to make our input. So that would be 1 in 10. Okay, so now that we've explained the algorithm, let's talk for a second about time efficiency. So our time efficiency is going to be big O of m times n. M is going to be the number of denominations, and this is going to be times n, which is our amount. So in that case, the number of denominations would have been 3, and the amount would have been 11. So the time efficiency for that one would have been 33, or big O of 33. Let's go ahead and talk about the space efficiency. So the space efficiency is just going to be big O of n. And n is because we had to create an array for the algorithm. So overall space efficiency is big O of n, and then our time efficiency is big O of mn. Overall, it's quicker. It takes a little bit more space than what we learned with the greedy algorithm in chapter 9. However, the time efficiency is much better. So now we know the change making algorithm, and we know how to give him the correct amount of change for next time. Have a good one.